Okay, now, in the last example, we had to interchange the columns and rows to basically turn the matrix in a way so that the first row was, or excuse me, the first column was the first row, second column was the second row, and so on. And then we did our row operations. So what was that step that we were doing? What do we call that? So this is where we're going to define that. And so we define that as the transpose of a matrix. So the transpose of a matrix is the result of interchanging its rows and columns so that column J of matrix A is row J of A transpose. So this T, that's another, this is the way we denote it, the transpose of a matrix. It's A with this superscript capital T, so that means the A transpose. So it's a different matrix, okay? So in other words, we could say we're transposing A into matrix B like we did in the last example, but B is actually A transpose, okay? And so, so again, it's the result of interchanging its rows and columns so that column J of matrix A is row J of A transpose and vice versa, okay? So, what else? So based on this, we can summarize what we did in the last example as transposing, then reducing, and then transposing back. Okay, and I think that's all I want to say. Okay, so we can even, at the price of tolerating the vague idea, the as-yet vague idea of vector spaces being quote-unquote the same, we could use Gauss's method to find bases for spans of other types of vector spaces. In other words, in this case, column spaces. All right.